If I have an object at rest, clearly it has no velocity and it has no momentum. If I want to get this object to accelerate, I have to exert some type of unbalanced force on it, and Newton's second law will allow you to calculate that acceleration. So I exert an unbalanced force, and the object accelerates. However, now you know that when an object is accelerating, that means its velocity is changing, and momentum cares about velocity. So by exerting this unbalanced force, I am also causing the momentum of this object to change. In this scenario, it goes from starting with zero initial momentum to having some final momentum value that is not zero, that is in some way related to the acceleration it experienced, which is then related to the amount of force that the object experienced. If I want to get this object moving fast, there are a couple different ways I can do this. The first way is to exert a large force for a very short time. And the other way I could do this is by exerting a smaller force for a slightly longer amount of time. And the goal of today's investigation is to kind of tease out how force, time, acceleration, velocity, and momentum all work together. Part 1 of this lab involved looking at how force changes momentum in the presence of a constant force. And to do this, I elevated one side of this track to create an incline. Objects on an inclined plane experience a constant force that is called the parallel force that is directed parallel to the surface of the incline, and the instructions tell you how you can calculate this force. In this part of the lab, we started with the cart toward the top of the incline. I'd press play on Logger Pro. I have a motion sensor right here that is prepped to take velocity data. I press play, get ready to record velocity, and I let go. And the cart accelerates down the incline. I then use the velocity versus time graph in Logger Pro to analyze my data. This is what the setup in Logger Pro is going to look like. I have the velocity versus time graph, which I get the information from the motion sensor, and I have a force versus time graph down here, which information I get from the force sensor. In part 1, I'm not using the force sensor, so I'm just going to ignore this bottom graph. But this velocity graph is what a good trial would look like. I pressed play, and then a little moment later, I let the cart go. Because the cart on the incline experienced a constant force going downhill, the cart moved with a near constant acceleration, as shown by the straight line on the velocity versus time graph. And then to get information, I clicked and dragged to highlight a little bit of the velocity versus time graph, and I just had Logger Pro tell me the statistics for this area, and what I care about here is the max. The max velocity value is what I would plug in for my final velocity. And then to get the time, I clicked and dragged for the interval over which the cart was speeding up. Where the cart starts to slow down, here was where it reached the end of the track and it hit a bumper to slow down. So I wanted to click and drag for the whole region that the cart was accelerating. And then right down here, Logger Pro tells me the statistics here, and what I care about is the delta t. The delta t tells me how much time it took for the cart to actually go down the track. Part 2 of the lab looked at how force changed momentum when the force was not constant. To do this, I laid the track flat on the table, and instead of calculating the force like I did in the previous part, I used a force sensor to actually measure how hard I was pulling the cart. In these trials, I would start with the cart close to the motion sensor. I did 2 trials where the initial velocity of the cart was 0, and 2 trials where the cart already started in motion. I would press play in Logger Pro, and I would give the cart a pull to accelerate it. And Logger Pro would both simultaneously take velocity readings as well as force readings, which I could then use to calculate momentums, change in momentums, etc. So this is what a good trial in part 2 of the lab would look like. So this time I used the force sensor to take force data, and I really just pulled. You actually can't do this wrong. I pulled. You can see my force was a little erratic, definitely wasn't constant, and that's totally fine. I highlighted the region of the graph where you could tell I was pulling. And then I went up here and I used what is called the integral function, which gives me the area under this graph, which is the same thing as multiplying the force by the time. And then I go up to my velocity graph, and you see that because my force was not beautiful and constant like it was in the previous section, that my velocity graph is not quite as nice and linear. No big deal, that's the whole idea. So once again, I kind of highlighted a region of the graph, and I kind of highlighted a region of the graph that aligned with the end of me pulling. So this is when my force stopped acting, which is when the cart should have been moving the fastest. And I found the maximum value for that region. So that gives me my final velocity. And then once again, I go down to the force graph, highlight it, take the area under the graph, the integral, and then this number right here gives me the area under the graph.